Hello, I'm going to present a paper with the title No Reference Video Quality Assessment by Deep Feature Maps Relations. First of all, what is video quality assessment? Simply, we can say how a particular user perceives a video, whether it is of poor, medium, or high quality, which is stated using scores ranging from 1 to 5 or 0 to 100 depending on the dataset. But why do we need VQA? The main reason is videos are increasingly becoming ubiquitous. We can see videos everywhere, and some examples are video streaming applications, which include news, entertainment, education, and the others. To name a few, YouTube, Netflix, and so on. Second example, video usage in social network apps such as WhatsApp, Telegram, Instagram, and the other local famous apps. And video surveillance, which is widely used to supervise, ensure safety, security, and something like that. And there are two techniques for video quality assessment. The first one is subjective, and the second one is objective. Subjective video quality assessment is the most accurate technique, which determines how a particular user views a video and rates it. Subjective scores, or MOS, subjective video scores are also known as MOS, or mean opinion scores. And in order to obtain this, a video is rated by experts in a specified range, and their scores are then averaged. And the objective technique. In the objective technique, the scores are automatically estimated using some computational models, and these models actually estimate the MOS, or mean opinion scores. There are some challenges in subjective video quality assessment. First of all, they are time consuming, so they cannot be part of real-time apps. And secondly, they are expensive because they require room, appropriate equipment, experts, and the other things. So they're expensive. And the third challenge is they're not always accurate because they depend on the physical condition, personality, and emotional state of the observers, because observers are human after all. But what are different methods for objective VQA? The first one is full reference. In the full reference, there is a reference video and a degraded video, and the quality of the degraded video is evaluated after comparing these two videos using some metrics and using some approaches. And the second one is reduced reference. In reduced reference, only partial information of the reference video is required. And the second method is no reference, in which there is no reference video, and the quality of the degraded video is predicted without access to the reference video. And why do we address no reference? The answer is the pristine video was not available in most applications. There's no reference video, actually. And the other reason is prediction of no reference video quality, specifically in UGC or user-generated contents, remains largely unsolved. And they're not accurate. They're not as good as the ones in full reference method, actually. There are two types of VQA datasets. The first one are synthetically distorted. They are older and more traditional datasets. And in order to provide these datasets, there are some video references, and some degradations are applied to these references. And these degradations include compression, ringing effect, blurring, and the other artifacts. And some of the most famous synthetically distorted datasets are Live, CSIQ, EPFL, PolyMI, Live Mobile. And What about authentically distorted datasets? They're also known as user-generated content, or UGC, or end-of-white videos. In such datasets, no video references are not available. And these videos are typically produced by ordinary users which are using their gadgets, such as mobile devices, camcorders, and these video creators are not professionals. They're amateurs, and the video is not a professional one. And they contain a wide range of degradations. Some of the most famous authentically distorted datasets are COMVID1K, LiveVidUC, and YouTube UGC. And the no reference video quality assessment methods. There are three main approaches. The first one is deep learning based methods, and the other one is handcrafted features based, and the second one is ensemble. In the deep learning based models, as it can be inferred, features are extracted using deep neural networks, features of clips or frames or images. And in the handcrafted features, some features such as NSS, natural scene statistics, optical flows, motion vectors are used as frame level or video level features. And the ensemble features use best of the both worlds. Here we introduce the proposed method, and our method includes three steps. The first step, in which we get frame level features. In this step, we extract feature maps from mid layers of a CNN, for example VGG19, and then we get gram matrices from those feature maps, and then by vectorizing the gram matrices, we will have a frame level feature. And the second step, we have to convert the frame level features to the video level features by pooling, and we use max pooling in order to convert the frame level features to video level features. And in the second step, we will have regression. And in order to do that, we use an SVR to map video features to quality scores. And in order to train the model, we use fivefold cross-validation, which is repeated 10 times. And we will have 50 correlation scores. And one important point is, in order to evaluate the performance of our method, we use two famous metrics, which are SROCC, Spearman Rank Order Correlation Coefficient, and PLCC, Pearson Linear Correlation Coefficient. These are two types of correlation which are widely used in the world of quality assessment. But what is gram matrix after all? In order to have a gram matrix, we use feature maps of a specific CNN layer and then vectorize the feature maps, and stack them together, and we will have a matrix. And as depicted in the picture, we will multiply the obtained matrix by its transpose, and then we will have the gram matrix. But what this gram matrix shows? Actually, it shows the correlation between feature maps and provides structural relationships that includes useful information about texture, color, and curvature in the image. And that is the heart of our method. In the previous methods, they have mostly used the features that are obtained from the last convolutional layers, and these features, such features mainly indicate patterns available in the image, available in the frame, and actually using those patterns and using the changes in those patterns, they evaluate the quality of frames and images. And here we are using totally different features that are firstly used in order to evaluate the quality of a video or quality of images. And as I said, this is the heart of the method. And by analyzing the relationship between the details of different granularities in the image, we can have useful features. And by granularities, actually, we mean texture, as we have coarse texture, fine texture, and these different textures help us to evaluate the quality of a frame and then a video. And using those correlations that I stated in the previous slide, I mean SROCC and PLCC, we evaluate the performance of our method. In VGG network, VGG19 network, we have 5 stacks of convolutional layers, conv1, conv2, up to conv5. And in each of these stacks, we have several convolutional layers. For example, in the first stack, we have 2 convolutional layers, and in the 5th stack, we have 4 convolutional layers. And here we can see by getting gram matrices that are obtained by the feature maps of the mid layers. I mean conv3, we will have the highest SROCC. So by getting the features, by getting the gram matrix from the mid layers, we'll have the best values. And here we compare our method with those handcrafted features, with those handcrafted based methods, or those deep learning based methods that haven't used fine tuning. And here we can see that the VSFA method lies in the first place, and our method lies in the second place. And in the next slide, we have compared our method with those deep learning based methods which have used fine tuning. And in this table, we can see that PVQA method lies in the first place, and again, our method lies in the second place. How well? And in the last slide, we can see the correlation between the predicted scores and the ground truth MOS. Actually, the horizontal axis shows the ground truth MOS, and the vertical axis shows the predicted score, and we can see how well these two values are correlated. Thanks for your time, and in case you have any questions, I'll be glad to answer. Thank you.